Welcome back to continue section 5.2. So today we're going to start talking about the zeros of a polynomial. So far we've learned how to classify them, we've learned how to find the relative max and mins. Now we're going to talk about the zeros of polynomials. All right, now the zeros of a polynomial it actually has many terms. We can call it a zero, a solution, a root. Those all mean the same thing. They're synonymous for finding that same thing, just depends on how you're looking at it, okay? A solution is when you're trying to find the solution to the equation. A zero is when you're looking at the function graphically. So it depends on just how you're looking at it. Now, what does it mean to talk about the zeros of a polynomial? Now, in factored form, finding the zeros is actually really easy. So finding the zeros, basically what it's talking about is finding what would make the y 0. What x's would make the y 0. And again, if you're thinking about that, what you're really talking about graphically are the x-intercepts. Because remember, x-intercepts are when y is 0. You're finding the x's that make that happen. All right? So here, what does that mean? Well, what that means is I need to figure out what makes x plus 2 equal to 0. I need to find, well, what makes x minus 1 equal to 0. I need to figure out what makes x minus 3 equal to 0. So in factored form, it's literally just looking at each piece and figuring out what makes it 0. Well, here, these ones are hopefully really easy for you. Okay? Most kids see this without a problem. Okay, if I'm asking for the zeros and I already give it to you in factored form even, most kids can rattle off right away, oh, -2, 1, 3, boom. Okay, now there are a couple tricky points in here though that I need you to be aware of, okay? First, one that somehow kids can kind of mess up and forget is what if there's an X out front? Okay, if there's an X out front like this, well, it just has to be 0 in and of itself. And then the whole thing would become 0, right? So that one is actually surprisingly the easiest, but it has been known to kind of catch kids up. So do make sure you're aware of that. An X sitting out front of all the parentheses, all that means is a 0 would make the whole thing 0. This one right here, again, I think pretty quickly you guys would pick up on. A -4 would make that whole thing 0. Now this one right here, that one takes a little bit more math, okay? That one isn't quite as obvious to students what it is. So I do encourage you, for ones that are a little bit more complex, do actually show the work of, all right, I want to know what could potentially make this 0. And actually work through it, okay? So now let's just take a moment here, okay? Because I just found all of those zeros, but I want you to know what they are, okay? So I want to show you graphically what we just found. All right, so what we just found here is we found x minus 1, x plus 2. I'm going back to the previous one, x minus 3. So I do want you to have an understanding of what are we finding? Well, what we're finding is where that polynomial crosses the x-axis. That's what I mean by zeros, okay? Graphically, we're looking at those crossing points, okay? So just again, just so you kind of understand what we're looking at when we're finding these things, that is exactly what it is. We're finding where it's crossing the x-axis, all right? So now it does get a little bit trickier though, okay? Because I could give you something like this and say, hey, find the zeros. Find when y equals 0. And now notice this has an added piece. This has exponents in it. Okay? What those exponents are is they're called a multiplicity. Okay? And a multiplicity, basically it affects how many times is that factor represented in the polynomial. Okay? So for example, this one, that has a solution of 1. So which is 0 is 1. It is represented twice in the equation or in the formula because of that square. And that essentially, I'll show you on the next slide, that impacts how the graph behaves around that 0. Okay, and again, we'll come back to that in just a moment. Here, that one has a solution of -5 and an exponent of 1, so its multiplicity is just 1. That has a solution of -4 and an exponent of 3, so its multiplicity is 3. It's represented 3 times in that equation. So that's just the added thing, is all of these have multiplicities. If it's not shown, it just means it has a multiplicity of 1, an exponent of 1. All right? And of course, we can do the same thing over here. Remember I said whenever there's an x out front, it means it has a solution of 0. But this time, it has a squared on it, so that means it has a multiplicity of 2. That has a solution of -7, and again, if there's no exponent showing, that is implying a multiplicity of just 1. That one, remember, that takes a little bit more scratch work. If I want to know what is actually going to make that 0, then do the math, add the 5, divide the 2. So this one is going to be 5/2, and it has an exponent of 5, so its multiplicity is 5. Okay, now what are these multiplicities doing? Well, what they're doing is they're showing how the graph behaves. So here you can see your solution at -1, and you have a solution at 3. Okay, so graphically, you're looking at the x-intercepts when you're finding those solutions, right? Now, that first one of -1 is called a double root. It has a multiplicity of 2. So notice what it's doing. Okay, notice it comes up to the 0 and it turns right back around again. Okay, so the unique thing about that is even multiplicities make it act like a quadratic. It'll touch the 0 and turn back around. Instead of when it's an odd multiplicity, it just passes right through. So those multiplicities are a very powerful idea because if you're graphing these without a graphing calculator, which I won't make you do, but in college they can, I've seen it happen, it really helps you know what the graph is doing if you are aware of those multiplicities because it shows you the behavior that the graph is going to have around it. Okay, so let's take a look at these. So what if I wanted to find the zeros of these things? Scary, but still possible, right? If I want to find where the zeros are, well, remember, so far we've been working in factored form. So quite literally, all you have to do is factor. Oh, not 6, I'm sorry. X plus 10, x minus 2. So this will have a 0 of -10 and a 0 of 2. So remember, you can also do this, accomplish this without having it in factored form. Here, you get that, which is the same as that. And whoa, look at this. So this has a solution of 7, right? And it has a multiplicity of 2 because it's represented twice because of that exponent. Okay, so the same rules apply to all polynomials, but today just the focus is I'm giving you the factor form already. But again, you know how to do this even when it's not. It just means you have to do the factoring yourself to figure out what those zeros and multiplicities are. All right, now the other really cool thing, is if I give you the zeros, you can actually therefore reconstruct the polynomial that made it, okay? Which sounds complicated, but it's actually really doable, okay? So a 0 of 4 basically means that my polynomial needs a factor of x minus 4. If I have a 0 of negative 5, it means that I must have a factor of x plus 5. So notice between the 0 and the factor, notice that there is a sign change there, okay? For example, a factor of 6, or a solution of 6, means I have a factor of x minus 6. Solution of negative 7 means I had a factor of x plus 7, okay? So here, just notice that sign change. But I can use those zeros to reconstruct the factors to reconstruct the polynomial. So let me show you what I'm talking about. Write a quadratic polynomial standard form with zeros, 3, and negative 1. All right, so a 0 of 3. 0 of 3 means I would have a factor that looks like that, a factor of x minus 3. A solution of negative 1 means I'm going to have a factor of x plus 1. So all I'm going to do, I'm going to use those zeros to reconstruct the factors. Now notice it says standard form. So standard form, how do I get there? Well, that means I'm going to have to FOIL this thing out. X times x is going to be x squared plus x minus 3x minus 3. So there is my polynomial that has those 2 zeros. Okay, again, really cool that you can do this. All right, use the zeros to reconstruct the factors, FOIL out the factors, and that gives you the polynomial. All right, so this one, that negative 2 means I have a factor of x plus 2. That 2 means I have a factor of x minus 2. And the 3 means I have a factor of x minus 3. So I can give you ones that have a little bit more, okay? Now here, my personal recommendation is any that are the same but opposite sign. Those are the ones you want to FOIL together first, because again, to get to standard form, you need those things the same, okay? I need to FOIL this out. So FOILing that out gives me x squared plus 2x minus 2x minus 4, right? X squared, 2x minus 2x, negative 4. I haven't done anything yet with that other one, okay? That one I'm going to leave alone for now. But notice the reason I combined those other two first is notice kind of the cool thing that happens. That middle cancels out. Okay? So now I have this. And So you may be wondering, well, it's not a standard form yet. And I would say, yes, you are correct. However, the neat thing that happens here is I can FOIL this again. All right, so let's do that foiling process one more time. So here, that's going to give me an x cubed, because x squared times x escalates it up to x cubed. Then I have minus 3x squared minus 4x plus 12. And this time, I don't see any like terms I can combine. They all have different powers. So what that means is this is already done. Okay, so just keep in mind for cubics, you are going to have to FOIL twice. Keep that process going. But as long as you're kind of clever about it, sometimes you can make the foiling not end up as that bad. Okay. All right, so there is one like this though. So what about this? A 0 of 1 with a multiplicity of 2. So what does that mean? Well, that means I have that factor, but having a multiplicity 2 means it's represented twice. I have 2 of that same factor. And then a minus 3 means I have an x plus 3. All right, so now when I go to do this one, I'm just going to pick 2 and I'm going to FOIL them together. So here x squared minus x plus 1. Let's clean that up a little bit. X squared minus 2x plus 1. So this one didn't turn out quite as nicely, did it? So in this instance, we can't really exactly FOIL again because we don't have two binomials, but we can kind of adapt that process to keep it going. So what I'm going to do here is to finish the process, I'm basically going to send out this x to everything. So I get x cubed minus 2x squared plus x. Now remember, you can do the same thing with the 3. Plus 3x squared minus 6x plus 3. Okay, so remember this back from Expo, that the foiling process essentially works in this way. This is how you have to do it if one of your terms is more, or if one of your factors is more than a binomial. So this gives me x cubed plus x squared minus 5x plus 3. Okay, so still the idea of foiling twice, just that second foiling looks a little bit different when you have to do it this way. Okay, but again, general idea is the same. Just reconstruct your factors and then FOIL it out from there. All right, so let's start putting all of this together, okay? So let's start looking at what does this mean. So actually, let me scoot this up because we're going to use that polynomial to have a conversation about some of these other aspects, okay? So let's name this polynomial based on its degree. Well, it's degree 3, so this polynomial is a cubic. Its number of terms, 1, 2, 3, 4. It has 4 terms. Well, remember that one doesn't get a special name. So it's just a polynomial of 4 terms. Its end behavior. Well, its end behavior, notice it's odd and positive. So think of a line with a positive slope. It's starting down at the bottom and working its way up. So its end behavior is going to be down, up, relative max and mins. So for that we're going to need our graphing calculator. Okay, so let's go to our graphing calculator. Y equals, let's type in what we have. So x to the third plus x squared minus 5x plus 3. All right, and I see something like that. And I want the max and mins of that function. So here's my relative max, here's my relative min. So let's go through that process and making sure we remember how to find them. Let's start with the max. So remember, we go into calculate because we're calculating the maximum. Go down to max, and remember it's going to give me some prompts, left bound. So that means I want to scroll over until I'm to the left of that point, then scroll over until I'm to the right of that point. I'm going to hit enter one more time, and there is my maximum. So my max point is negative 1.6 repeating. So my max is at negative 1.6 repeating and 9.48 approximately. Okay, you can round to 2 decimal places. So if you don't want to use that notation, you could just call this 679.48. Okay, just round to 2 decimals for me. And the minimum. So again, now I want to calculate the minimum. So I just want to scroll over. So I'm a little bit left, which I am. Scroll over to the right. Hit enter one more time. And remember this, that's just kind of gobbledygook that represents 0. Okay? So really the point is going to be 1, 0. And there you have it. So don't forget those old skills that we've been working on, because all of those are obviously building towards what we're going to need to know for our test. So please make sure, now that we've gone through all of this, write that summary for me. Reflect on what we've talked about, and then make sure you come back and ready to do your practice work.